Right, okay, so last time we were talking about directional derivatives, and here's what we finished with. We have this definition of this thing called a directional derivative that uses this notation, and it has various different interpretations that we get to use. I can think of it as how fast the function's changing if you're moving with velocity in a particular direction at unit speed, right? It's computed with a dot product with the gradient. You can think of it as being slope of a graph, and you can think of it as being a multiplicative factor, as a result of which, being as it is a multiplicative factor, you can think of it as being df/ds, or rate of change of the function with respect to distance, which is a really nice interpretation. All right, so that's where we left it last time. We'll do a couple of examples here. First example, notice it says, what's the slope of the graph? Well, that's just right down the pipe, isn't it? Slope of the graph is one of our interpretations of directional derivative. So before we even read the rest of the question, we know our answer is going to be a directional derivative. Right? Okay, now function is given, point to evaluate is given, blah, blah, blah. Okay, so slope is a directional derivative. Directional derivatives are computed with this formula from the previous page, again, already established. Okay, so one little subtlety on this question is you'll notice that I need to be doing a directional derivative. Directional derivatives certainly, no matter which camp you are in about what the definition should be, right? The slope requires that this be a unit vector. And now notice we were not given a unit vector. We were given this vector 3, 4. I'm interested in the direction that that vector points. This has both a direction and a magnitude. We want just the direction. Specifically want the unit vector that points in that direction. And of course the way we find a unit vector that points in a given direction is you divide your vector by its own magnitude. Okay, so there's that. And with that established, again, let's see here, our slope is a directional derivative, which is a dot product, and we just got through computing our unit vector there. And what remains then is to compute the gradient. So the gradient, take the appropriate partials, plug in the point 3, 1. That's where you need to evaluate this gradient. And the gradient ends up being that right there. So notice then all together, we're just going to do this dot product. Here, my picture's getting a little awkward here. Our directional derivative is just that dot product. Arithmetic. Everybody happy? All right, now I want to call your attention to a point of language and interpreting what that language means. It says, in the direction of the vector here. Now, it explicitly says vector. Notice that, right? But I'm going to point out, we don't even really need to have said vector. If I had said in the direction of 3, 4, then let's ask, just, again, context should always make it clear whether this is a point or whether this is a vector. And, well, it says the direction of. Points don't have directions, right? Points have locations. So even without having explicitly said that this is a vector, direction of 3, 4 means interpret 3, 4 as a vector and then find the direction that that vector points. Now that said, some students perhaps just interpreting language a little bit too casually will misinterpret this as meaning toward the point 3, 4. And this is really importantly not right. This is not what this says, right? So let me put an X through that. These are not the same thing. And you can see explicitly how, if you were to make the mistake of making this interpretation, let me draw a picture here. XY plane. We're starting at the point 3, 1. That's about here, let's say. And now let's see. The correct interpretation was in the direction of the vector 3, 4. 3, 4 would be about like this. Yeah, something like that. It's not to scale, exactly. But toward the point 3, 4, the point 3, 4 would be about here. So if you misinterpret, you'd find yourself going that way, which is wrong, instead of going this way, which is right. Does everybody see the potential, the risk, right? The landmine, how if you misinterpret the language, you're just going to be going in completely in the wrong direction. Okay, something to be careful about. Okay, next question, next example. We have one of these situations that we see a lot where temperature is a function of position, right? One of my favorite examples of a function of 3 variables because it's kind of relatable, physically relatable to, we move around in 3-dimensional space a lot and notice different temperatures, right? So it's relatable in that sense. Excuse me. And the question asks, at a certain point and moving in a certain direction, what is dTds? And again, this is one of our stated, established interpretations of directional derivative, right? So details to be worked out, sure, but right off the bat, as soon as we see rate of change with respect to distance, we know we're talking about a directional derivative. We know directional derivatives are computed with dot product with the gradient. So again, we've just got to kind of work out some little details here. So the details in question, let's see here. I need to know what my gradient is. So I've got to take the appropriate partials. Now, this is a healthy exercise. Make sure that you're comfortable with what I did here algebraically to compute that gradient, right? You might want to look at it after class or whatever, but that's what the gradient is. But it's a little you got to think that through, right? We plug in the point as before, and altogether, then our gradient at the point we're interested in is this thing that goes right there. Again, we have to figure out what the unit vector is. Again, the unit vector is the given divided by its own magnitude. Notice, again, we were given not a unit vector. So that's why you have to divide by the magnitude. And again, you dot product, arithmetic, simplify, and there's your answer. Everybody okay? Okay, make sure you can do the little details here. Very important little issues. Okay, now I have a sad story about convention. Unfortunately, not everyone agrees on what the proper strict definition of directional derivative is or should be. In most of the textbooks that I've seen, the word directional derivative is defined as exactly what I wrote here. And let's see here. Let me I'll do it like this. The directional derivative is defined as only for unit vectors. V has to be a unit vector. And in that case, with the definition requiring that we have a unit vector, then that expression and and it's a slope and it's a multiplicative factor and it's df ds, just like we talked about. Okay. There are people, I'll say, who are of a mind to eliminate that requirement. Why should that have to be a unit vector? And in fact, even if you throw that away, it remains that these two things are still equal. And these two things are still pretty handy. How fast is the function changing? Very natural. Perfectly natural thing to want to talk about. This dot product of the gradient still computes the answer to that natural question. And those people still use the term directional derivative, and they still use this same notation. Now, the bad news, you do have to pay a cost, right? If you want to give yourself the increased flexibility of allowing yourself to have non-unit vectors, the cost is that what you compute is no longer a slope of a graph. It's just not. And it is no longer a multiplicative factor in the usual sense. And so that's the price that you pay. You can't have that anymore, right? But there are those out there that would use the term directional derivative in the sense that I have highlighted sort of in purple here. And sadly, this is an under-discussed discrepancy in my experience. Textbooks present this as just matter of fact, no asterisk or comment or anything. And then if you go talk to certain mathematicians, they say directional derivative for non-unit vectors, and well, of course what do you mean it's got to be a unit vector, right? They don't know where are you coming from, right? So there's an underappreciated potential for misunderstanding. So the reason I'm mentioning this to y'all, the reason I want y'all to understand this, I can't see there it is. The reason I want y'all to understand this is that it's kind of on you to figure out who you're talking to. Right? If someone says the term directional derivative, heads up. What kind of a person is this? Is this a unit vector kind of person, or is this a general non-unit vector kind of person? And they might not realize that you don't think it's perfectly obvious which one they are. Right? Now, just for full disclosure, let me say it this way. For Math219, we have a very crisp answer to this question. In Math219, we are going with the green definition. In Math219, directional derivative means unit vector, and you get all of these goodies just as we spent time discussing and just as we used in our examples and applications. In this course, that's what directional derivative means. Outside this course, heads up. And by the way, for whatever it's worth, outside of Math219, I'm one of them. I'm a non-unit vector person outside of Math219, but in Math219, no. Does that all make sense? Is everybody on board? Yes?
If you don't use the unit vector, then what would dBF represent?
It represents how fast the function is changing. And in other words, what you might view as being df dt. So derivative with respect to time, right? Which, again, it's a natural thing. Now, it's not the only natural thing to want to be interested in, but it is something that's natural to be interested in, and it's computed with this very simple formula. So, yeah, that's, pretty good motivation to want to do it that way. Yeah. Okay. All right. Now, next question. We're going to find that there's some really interesting answers to some really interesting questions that come up when you talk about directional derivatives. And here's the first one. We're just going to dive in on these. Supposing that we are at some point A. By the way, notice that I've got a function that's real valued multivariable function. Notice I'm looking at the literal picture here, as I like to call it. You can see the domain. You can see the target. We are going to ask a question, which is, if I were to start moving in some direction in the domain, unit vector, of course, this being Math219, right? Unit vector is going to represent a direction. And I would like to ask, as changing in the input will cause a change in the output, and we know that the rate in the output is the directional derivative, of all of these possible different unit vectors representing different, different ways that I can move in the domain, which one makes this directional derivative as big as possible? That's a pretty reasonable question. There's lots of scenarios where this would be reasonable. Here's the obvious, low-hanging fruit example. Suppose this is me, and the function represents temperature, and I'm cold, and I don't like being cold, and I want to move to where it's less cold, right? So I'm here, and I'm contemplating all the different directions that I could start walking or running, depending on how cold I am. Which direction should I be going to make my rate of change of temperature as high as possible, right? I don't want to walk in some direction where the temperature is barely increasing. I want to maximize my rate of increase. Does that make sense to everybody? Okay. All right. Okay, so now before we answer this question, I want to talk a little bit more about how to interpret the question, and there's some terminology here. Keep in mind, directional derivative represents rate of change with respect to distance. Okay, this is one of our interpretations of directional derivative. How fast the function changed per unit distance. Okay, so if we find the direction, let's hypothetically, let's suppose it's that way. If we find the direction that makes the rate of change of the function as great as possible, wouldn't it be reasonable to call that direction the direction of fastest increase? After all, this is the direction that makes the function increase as fast as possible. So, direction of fastest increase. That make sense to everybody? All right, now, alternate interpretation. Also perfectly reasonable. Another interpretation of directional derivative is that it is the slope of the graph. Right? Now, again, let's kind of think it through. What would we say about a direction that makes the slope of the graph as great as possible? Well, if I go in this direction, maybe it's only got us that much slope. Right, so it's somewhat steep in that direction. But if I were to move over to a different direction, maybe it's steeper as I go in that direction. Right? So the direction that makes the steepness as great as possible, wouldn't it make sense to call that the direction of steepest ascent? In other words, as you go in that direction, as you hike that way on the map, that's the direction that's as steep as you can make it. It's what you might call uphill. Yeah? Everybody happy with that? So these two terms are both out there. I think they are. They both have their place. Direction of fastest increase, the direction of steepest ascent. Cultural point for y'all. The most common term is this one right here, direction of steepest ascent. You're going to hear that a lot. Outside of my lectures anyway, direction of steepest ascent. Here's the problem with it. Direction of steepest ascent comes from the idea that directional derivatives gives you slopes, but wait a minute, they only give you slopes if you're looking at a graph. What if you're not looking at a graph? How useful is it to think about the thing you're dealing with as being a slope if you can't see it as being a slope because you're not looking at the graph? I think that's confusing myself, right? So despite this being the more common term, I think it's got a lot of potential for confusion, while this one here doesn't. It doesn't matter what kind of a picture you're looking at. This direction that makes your directional derivative as great as possible is always the direction of fastest increase. Whether you're looking at a graph or whether you're looking at this literal picture or whether you're looking at a bunch of level sets, basically you're looking inside of the domain, whatever. The function is increasing as fast as possible when you go in that direction. It just always makes sense. So I go against the flow on this one. I use the term direction of fastest increase. I wasn't raised to use the term direction of fastest increase, and I have a reflexive sort of, sometimes I'll say direction of steepest ascent, but I kind of always kick myself when I do. I think the direction of fastest increase makes more sense. Anyway. Okay. So, moving along. How do we compute it? Here's what we're trying to maximize. Directional derivative. We want to make that as big as possible. Directional derivatives are computed as a dot product. Cool. We want to make that dot product as big as possible. Oh, don't forget, dot products can be computed as magnitude times cosine of the angle. That's an old linear algebra formula relating to dot products. This is what I therefore want to make as big as possible. Don't forget, V has to be a unit vector, which means that this magnitude here is 1, and thus that magnitude we can throw away. It's a factor of 1, it doesn't do anything. Okay, so this is what I want to make as big as possible. And even this, we're going to be able to simplify a little bit more as follows. Notice that the gradient is computed at this point where we're at. And notice further, whichever direction I'm looking, I haven't actually started moving yet. So no matter which of these unit vectors I'm looking, I'm still at the point A. So all of these factors, magnitude of the gradient, they're all in reference to the same gradient. They're in reference to the gradient vector at that point A. That doesn't depend on the unit vector at all. So this is a great big constant. So really, if you get right down to it, what do I actually need to worry about? What am I actually trying to make as big as possible? Cosine theta, and that's maximized when theta is equal to 0. Is that cool? Yeah. Okay, so that means that my picture is actually a little bit kind of off here in a sense. Keep in mind we are talking about, let's see here, yeah, so we've got gradient dot my unit vector v, and this theta here is the angle between them, but we just agreed that that theta has to be 0, and if you, again, looking at the picture, if that angle is 0, this angle is 0, I redraw the picture as follows. The picture is actually that. And so the vector that I'm looking for, this unit vector, it's the unit vector that points in the same direction as the gradient, for which we have this easy formula. So, okay, let's summarize what just happened here. We asked, what is the direction of fastest increase? Very natural question. And the answer is, it's the direction that the gradient points. All right, nice and crisp. Okay, next question. How fast is the function increasing in that direction? Right, I mean, this is the direction you go to make the function increase as fast as possible. How fast does it increase? What is this maximum possible rate of increase? Oh, all right, well, that rate of increase, directional derivative, computed with a dot product, again as usual. Keeping in mind, we just agreed that that maximizing vector is the direction of the gradient vector, so gradient divided by magnitude. And then you notice I've got gradient dot gradient, which is gradient squared. Magnitude of the gradient squared. And then you notice that that gives you magnitude squared divided by magnitude, and that's magnitude. So that's kind of weird that worked out this way. We've asked now two questions. What's the direction of fastest increase? And how fast is the function increasing in that direction? Extremely natural questions. And the answers are the direction of the gradient and the magnitude of the gradient. In some sense, the gradient is the answer to both of those questions. How about that? So I like to summarize that as follows. This is what I call a geometric characterization of the gradient. The gradient is the unique vector whose direction and magnitude are the answers to these natural questions. The direction is the direction of fastest increase. The magnitude is the rate of change in that direction. So what's weird about this is previously we've had a point of view on the gradient. The gradient was a formula. It was a formula that allowed us to kind of shorthand some otherwise tedious formulas. Right? And so basically we've been thinking of the gradient as being an algebraic tool. What we have now is I don't have to think of it as an object of algebra. I can think of the gradient as a geometric thing, right? The gradient is a thing whose direction and magnitude satisfy certain rules. And direction being fastest increase, magnitude being the rate of change. So think of the gradient. Now, we are now able to think of the gradient as being a geometrically natural thing. All right, example. Before I get into the example, I am going to talk about terminology convention a little bit here. Notice we have a surface that's in the shape of a graph, and a graph of a function of two variables is a surface like this, right? And I'm going to be talking about thinking of this as a physical thing, thinking of this as being a hill, and here's me standing on the side of the hill, right? That's what it would look like if you're standing on the side of a hill. You're on that surface. Now, how do we describe in practice, in the real world, right? How would I describe my location if I was there on that hill and I had a radio and I was talking to somebody who's, super far away and they want to know where I am? Then I would give them, for example, longitude and latitude. Right? That'd be a pretty reasonable way to describe location and sort of X and Y, if you will. Notice those are the inputs to the altitude function here. So I describe my location as being a point in the domain, but in reality, of course, I'm not in the domain. The domain's two-dimensional. I'm not in a two-dimensional world. I'm in the three-dimensional world. I have a z-coordinate, right? So it's kind of weird that we're in this scenario that, if I wanted to be really honest about it, I would have to describe my location as, well, I'm at a certain longitude, I'm at a certain latitude, and I'm at a certain altitude above sea level. But nobody does that, right? That would be silly. If you give map coordinates and say, I'm at the following map coordinates, it is understood that you're on the surface of the Earth. Right? So heads up about this. We're going to be using this convenient sloppiness. I'm going to be conflating these 2 points. Right? I'm going to be making reference to being at an X and a Y. And, well, of course, in reality, I'm actually at an X, comma, Y, comma, Z, but I'm not going to say it that way. Does that make sense to everybody? This is very common, so you need to be on the lookout for this. It is a confusing thing, and it's just that's just how people talk in these situations. All right. Okay. So, so let's actually do it now. So let's see here. I apparently am at this point 1, 3. Now, of course, again, 1, 3 is in the domain. I'm not actually at that point. I'm actually on the hill itself. Okay, but I'm going to say I'm at the point 1, 3. And the question asks, which way is uphill? For starters. So which way is uphill? Given that the hill is the graph of this function. Well, uphill, which direction should I go on the map to make altitude increase as fast as possible? What's the steepest direction? You might say, what's the direction of steepest descent? Right? What's the direction that makes altitude increase as fast as possible? What we're looking for is the direction that the gradient points. So merely from the fact that we want to know which direction is uphill, I immediately conclude that I just want to know which direction is the gradient. Now a little bit of algebra goes into computing that gradient. You know, you got to take various partials and plug in the point, etc. But the gradient at the point that I'm at, the gradient is that way, and that's southwest. And now just a little bit of context. On a map, typically the y-axis represents, like if you're looking at a map, right, a two-dimensional, you know, like this, right, the y-axis typically we think of as being up on the map. And we also, as a convention, most of the time, rightly or wrongly, make north up on the map. And so this is north. And with the understanding that this is north, then that green direction is southwest. Is that cool? Everybody happy with that? Okay. Okay, next part of the question, how steep is it at the point there? Well, how steep? What is the slope of the graph? What is DFDS? Again, the answer is the answer to the questions we were just asking, and it's the magnitude of the gradient, and that magnitude is 2 square root of 2. That's how steep it is. Everybody happy? All right. Okie dokie. Okay, let's talk about level sets. Oh yeah, question. Sorry.
Question. So my question is, like, if it was inverted and it was like if we're looking at a crater, and
yeah,
would that be like would the direction be like the direction of greatest ascent?
Yes, and that would be sort of out of the crater.
Oh, it would be.
Yeah.
Ascent.
That's right. So if you're inside of a crater and you're kind of, you know, on the part of the wall of the crater, as it were, the gradient will point outward away from the center, indicating that you should go that way to go uphill. Yeah, totally. Yeah. So the gradient will always point what you might call uphill on the graph. Yeah. Good. Oh yeah.
Do we ever need to consider finding a slope that is, or slope or direction of ascent that is not the maximum with this?
Oh yeah, I mean sure. I mean, like if you're hiking, right? Sometimes you're interested in how steep is this trail that I'm on, right? And the trail rarely goes just straight up the mountain, right? That's usually too steep, and nobody wants to do that. And so they do that zigzag, switchback thing that we talked about before. Yeah, if you want to know how steep it is on the trail, then you need to know what is the unit vector describing the direction on the trail.
Set the direction to the direction you want, and it would.
And then you just compute the directional derivative. Yep, it's just straight up directional derivative at that point. Right. Okay. Alrighty. So let's talk about level sets. Now, point of contrast. Notice here we were talking about a graph. Right? So this picture that we were looking at was a graph, and remember graphs are, oh gosh, I've got a big mess. Let me get the mess out of here. Graph means a certain point of construction, and so there are certain ways to interpret graphs, and you always have to make sure to interpret pictures in the way that's appropriate to how that picture is made. We are no longer going to be looking at a graph. Now, as it happens, this is still a surface, but this surface is not to be thought of as being a graph of anything. Now, instead, in this case, this surface is a level set. And you can see right here in the way I have it drawn, F equals C. Right, so everything on this surface is a level set of this function called f. Now, if you note, this is a surface in space. Space has 3 different variables. Level sets live inside of the domain of the function. So that means that this is a very different kind of function than what we had on the previous page. This is a function of 3 variables because its level sets are surfaces which are represented by equations of 3 variables. Okay. Whereas on the previous page, f was a function of 2 variables, and we were looking at a graph. You got to keep in mind the context. Okay. All right, that said, I want to make some observations about how directional derivatives work, and I'm going to consider a scenario here where we're at a certain point, and let's suppose that I were to be moving along a curve like this that's entirely contained in my surface. Keep in mind, my surface is a level set. And I'm going to be moving along this curve. It's entirely on this level set. And now, so just to belabor the point here, that means the value of the function at every point, the value of f at every point on this curve is always c. Right? Because I'm in this entire curve is within this level set that says f equals c. So on that purple curve, f is constant. Right? Okay, well now if f is constant, now let me say that a little bit differently. If f is constant, that means that as I move in the direction that I'm moving, so let's consider a tangent vector there, that this green vector is tangent to my purple curve, and purple curve being in the surface, that means that this green vector is a tangent vector for the surface. As I move in that direction, as I continue to move along this curve where f is constant, f is not changing, aka the rate of change of f is 0. That's just a fancy way of saying f is still constant. Yeah? All right, so f, the rate of change of f is 0 for that tangent vector. And then I'm going to argue that you could make it likewise for any other tangent vector, whatever tangent vector you might happen to be looking at. Any tangent vector to the surface. Rate of change of f is 0. Okay, so what? Well, don't forget, df ds is what the directional derivative is. So if df ds is 0, that means the directional derivative is 0. And, well, of course, directional derivatives are computed with dot products. That means these dot products are all 0. Now, that's a heck of a statement there. Every tangent vector here, every one of these tangent vectors to the surface, its dot product with the gradient is always 0. Or, said differently, all the tangent vectors are perpendicular to the gradient. Well, orthogonal. All of the tangent vectors are orthogonal to the gradient. Is everybody on board? Everybody with me? And there's really only one way that's possible. If all of these vectors, all of these tangent vectors, they're all orthogonal to the gradient, well, then the gradient has to be perpendicular to the surface. Let's see here. Do it like that. Okay. The gradient perpendicular to all the tangent vectors, then the gradient is perpendicular to the surface itself. And this is the big punchline. Really cool fact. This is one of the main facts of what I will call the calculus of level sets, is that gradients, which are a very important object of calculus, right? Gradients are always perpendicular to level sets. And that perpendicularity is geometrically important. Is that cool? So again, one of the big points of the calculus of level set. So when you find yourself in any situation that you're looking at a level set, you've got yourself a really easy formula right here. Just compute the gradient vector. That will produce a vector perpendicular to your entire level set. Pretty cool. All right. So let me show you an application of that. Now, I know we already know the answer to this question. We've talked previously about tangent planes, and remember we viewed tangent planes as being graphs of linear approximations, and we have formulas, and that's all old news. I want to approach the question in a different way here. Keep in mind, it's not about the answer. It's about tools, right? Various tools we can use for various different things. So a different angle is going to be instructive. Reminder, if you have a surface that's a graph, right? And you want to interpret your surface as a graph, and you can talk about a, let's see here, a point in the domain, and you can talk about the point on the graph that's sitting above in the domain, and we have a formula for how to find our tangent plane. And again, that's it's the graph of the linear approximation. It's a formula. Look back in the notes. How else might I find the equation of that tangent plane? And here's the move. The move is to remember that even though this surface is given as a graph, I can interpret it a different way. I can reinterpret it as being a level set. It wasn't given as a level set, but I can choose to view it that way. The way I view it as a level set is this trick that we talked about some time back. This equation and that equation are, of course, equivalent equations. Basically, nothing happened in that algebra. And yet, what I have on the right-hand side, I'm clearly viewing this as being a level set. You can see right here, level set. So stuff equals 0, stuff equals constant. This is a level set of a different function. Right? It's an old trick from a week or two ago. Right? Every graph of one function can be rewritten as a level set of a different function. Cool. All right, now what does that do for us? How does that help us answer this question? Let's forget about all this graph business, and let's just notice that the surface in question is a level set. How am I going to find the equation of the tangent plane, given that this is a level set? Well, I just need to find a normal vector. This normal vector, think about it, the normal vector means that it's perpendicular to my tangent plane, which means that it's perpendicular to my surface, which means that it's perpendicular to my level set. Oh, wait a minute, we have a thing for that. You want to find a vector perpendicular to a level set? Sweet, gradient. Just take the gradient. Yeah. So you want to find that normal vector. The normal vector, you can just compute the gradient. And now, to be clear, you compute the gradient of the function whose level set you're talking about. So this function g, not f. My surface is the graph of f, but my surface is the level set, a level set of z minus f. Right? So not f itself. And so you compute the gradient, and it's kind of all downhill from here. Once you have that normal vector, the gradient being your normal vector, then in the equation for the plane, our normal vector is that right there. And the equation of the plane, yeah, you got to multiply some stuff out and move some terms around, collect some things, and what you get is our old, previously noted formula for the equation of the tangent plane. So, different way of coming at it, right? And so, as previously discussed, the big trick here, the thing that makes it all work, is that I took something that was given to me as a graph, and I reinterpreted it as being a level set instead. All right. There's an example here that the more times I teach this class, the more I sort of decide that this example that doesn't really serve much of a purpose. It's literally exactly what we did on the previous page, and you can see it right here. I'm taking what had been given to me as a graph, right? A graph of f, and I'm just reinterpreting it as being a level set by doing this algebra that takes that equation and turns it into this equation. That's exactly the same equation, right? It's nothing really, hardly anything happened there. Yeah, go ahead.
So, like right at the bottom where it says normal times x equals normal times x naught becomes this. How did we get that negative 12 on the right side?
So the that's right. So this negative 12 comes from this dot product. We use the gradient as the normal vector. And then the only other thing that we need is we need to have an x naught. We need to have a point on this surface that we know is on the tangent plane, and we're just going to use the point that we were given. Right. So we want to find the tangent plane. Now again, here's this conflation of two different things. In the domain, the point that we're talking about is 2, 1. But what that means on the graph is 2, 1. F of 2, 1, which happens before. Yeah. Okay. All right. Real quick, I want to talk about the question that we're going to answer next, and we're not going to be able to make very far into it. But we'll make more progress we'll finish this up next time. But I want to talk about what is the implicit function theorem and what is the question that it addresses. So here is a curve. Let's see here. In fact, I'm going to do it like this. This is an equation of two variables that gives me a curve. And now first I'm going to ask the wrong question, but it's sort of an easy wrong question, and that is this a graph? And the answer is nope, it fails the vertical line test, so it's definitely not a graph. That was easy. Okay, that's not the question. Here's the question. The question is, can I view this locally as being a graph? Let me explain what locally means. Locally says at a given point, such as let's look at this point. Let's look at this point right here. Right? Locally means that I'm going to consider only nearby points. I'm going to throw away all the rest of the curve. I don't care about any of that or any of that or any of this. I'm only going to look just at that one little vicinity, if you will, and considering only this little piece of curve right there, just this little green piece of curve. Is that local part of the curve, is that a graph? And what you'll notice is that yes, it is. Right, this passes the vertical line test just fine. Right, so this is what we mean by a local function, or it's locally can be viewed as a function. Is if you allow yourself to be myopic, right, and you look only nearby and ignore all the rest of the stuff. That is locally a function. Okay, now it seems kind of silly. Wouldn't this always work? I mean, certainly it works. Let's see here. Let me. So locally. Around that point, yeah, graph. Y is a function of x because it passes the vertical line test, no problem. And you can look at a lot of other points and everything's fine, but the problem comes when you look at this point. And that little piece of curve, let's look at this. Let's see, I'll do this in blue. This little piece of curve, again, still described by that same equation. Just this, looking only locally near that given point. Even locally, I still fail the vertical line test. Right? Look what happens if I try to play the vertical line test game. It intersects twice. And there's nothing I can do about that. By the way, when you say locally, the speaker who's making a claim about local whatever gets to make this little yellow ball as small as they want it to be. Right? And notice, no matter how small I make this little yellow ball, the curve is always going to be kind of wrapping under itself. And so even locally, we have a problem there. And we'll talk more next time about why we care about this and what to do about it. All right, see you later.